we can model it, but we cannot predict with precision where everybody's going to be at any given time.
Okay.
Because it's chaotic.
The chaos. So it's basically about the chaos.
It's about the
chaos.
chaos.
It's all about the chaos.
Yeah. So what we do is we model the chaos.
Right.
Right. We say this will be statistically looking like this over time. You're not going to track one object through the system for eternity. That's not going to work.
Here, we're talking about how a universe ruled by precise laws can still refuse to give us precise answers. Not because the laws crumble, but because tiny uncertainties get amplified by the machinery of those laws. Edward Lorenz learned this the hard way in the 1960s when rounding a number in a weather model, just at the third decimal place, produced a completely different storm a few days later. The equations hadn't changed. The information had. That's the key. In systems where small differences grow exponentially, asking for exact predictions becomes like asking a microphone to sing opera. It's the wrong tool. So what do we do in a universe that's touchy to initial details we can't ever know exactly? We step back from the single path and study the crowd of possibilities. Think of the asteroid belt. Most rocks there orbit peacefully between Mars and Jupiter. But at certain distances, Jupiter's tug aligns just right. Mean motion resonances that pump up their eccentricities a little each orbit until a safe path becomes a planet-crossing one. That's how we get the Kirkwood gaps. Depleted lanes sculpted by Jupiter's resonances, where long-term perturbations drive asteroids onto planet-crossing or ejecting paths. Add in the Yarkovsky effect, a tiny thermal push that nudges small asteroids over millions of years, and you have a conveyor belt that feeds hazards into near-Earth space. We cannot tell you which particular boulder will meet us in the year 2173. We can tell you how many should drift into dangerous lanes, and how their risk will change if, say, their spin flips or their surfaces darken. And here's the catch. That statistical knowledge is not second-rate. It's the basis for planetary defense. The same pattern plays out on grander scales. The solar system looks like a clock from a distance, but get close and you find gears with play in them. Mercury's orbit, driven by the subtle pushes of the other planets and the slight relativistic correction near the Sun, is chaotic over billions of years. Numerical experiments by Jacques Lascar and others show a small but real chance, on the order of 1%, that Mercury's path might be pumped into something wild far in the future, potentially destabilizing the inner system. Meanwhile, Saturn's moon Hyperion doesn't even spin predictably. Its lumpy shape and orbital eccentricity make its orientation tumble chaotically. You could measure Hyperion's angle with exquisite precision today and still fail to say where it will point a month from now. But not everything is chaos. The CAM theorem, Kolmogorov, Arnold, Moser, teaches us that in nearly integrable systems, many orderly paths survive as invariant tori, immune to small disturbances. That's why planets can trace near ellipses for eons. Those tidy regions coexist with chaotic seas and resonant chains. The TRAPPIST, one system of 7 Earth-sized exoplanets, showcases this. They are packed tightly, yet locked in a delicate, near-resonant choreography that seems to confer stability. The lesson is not that the cosmos is random, but that it's structured. Islands of predictability, channels of instability, and the currents that move things between them. So, how do we work in such an ocean? We abandon the quest to tag a single trajectory forever, and we evolve ensembles, swarms of slightly different initial conditions, to see how uncertainties spread. There's a mathematical way to visualize this. Imagine all possible states of a system as points in a high-dimensional space. Under deterministic laws, a cloud of points stretches, folds, and filaments. For Hamiltonian dynamics, Liouville's theorem says the phase-space volume of that cloud is preserved. It becomes so finely striated that any coarse measurement smears it, even though the fine-grained volume remains unchanged. That spreading is why local predictability dies and why global statistics become stable. The rate at which nearby trajectories separate defines a Lyapunov time, your practical horizon of certainty. For the inner solar system, it's about 5 million years. For weather, it's roughly a week. Different systems, same logic. This switch to ensemble thinking is why climate prediction works even when day-to-day weather does not. We can't say if it will rain on June 7th, 50 years from now. We can say that under a given greenhouse gas concentration, the distribution of heat waves, floods, and droughts will change, and by how much. Those are the numbers engineers, farmers, and city planners need. Similarly, when tracking potentially hazardous asteroids, we produce a corridor of future positions, not a single line. We then ask, what fraction passes through Earth's cross-section? Over time, that probability tightens with new data, just as a blurry comet sharpens when you bring a telescope into focus. And here's a twist that humbles us. Our instruments don't just measure, they set the limits of what we can know. Every bit of uncertainty we fail to pin down at the start becomes tomorrow's ignorance at a larger scale. Chaos has a measurable rate of information production. It tells you how quickly you must supply fresh, precise data to keep predictions sharp. That's why missions that ping an asteroid's position, or satellites that sample the atmosphere hourly, aren't optional luxuries. They're the fuel for foresight in a chaotic world. If this sounds like surrender, it isn't. It's a change of strategy, from prophecy to probability. Determinism in the equations does not guarantee determinism in our knowledge. Even where the dynamics are deterministic, exact prediction demands unattainable precision, and at quantum scales the future itself unfolds only as probabilities, not certainties. Once you accept that, you stop chasing certainties that don't exist and start optimizing the certainties you can have. Risk levels, likelihoods, confidence intervals. Air traffic uses that logic. Finance, when it works, uses that logic. Space agencies betting on launch windows, planetary defenses planning a kinetic nudge decades ahead, same logic. And here's the payoff. When you learn to see the statistical shape of chaos, you gain a kind of control more durable than false precision. You can anticipate patterns, design for ranges, and act early. You're no longer surprised that a calm asteroid belt can send rocks our way, or that a tranquil climate can shift its baseline. You're prepared, not for a single future, but for the family of futures the laws allow. The shift in perspective is simple. Laws of nature are promises about relationships, not guarantees about particulars. Know the relationships deeply, and you can navigate the uncertain particulars with confidence. That's how science turns chaos from a barrier into a map. Like if this was interesting and hit the subscribe for more.